Everyone knows about the quadratic formula. If you're anything like me, you've heard rumors of a cubic and quartic formula as well. You might have even heard that there's no quintic formula. And when you ask why not, you're told that it has something to do with Galois Theory, and it's never explained what that is. You might even have watched a few other videos on YouTube about Galois Theory, only to end up even more confused than you were to start with. These videos aren't bad, but I think most of them seem to miss the big picture, something called the fundamental theorem of Galois Theory, which is what I'll be presenting in this video. Hopefully by the end of this video, you'll be able to see why we cannot generally solve quintics. When I say that a polynomial is solvable, I mean that you can write all of its roots, that means the solutions, in terms of radical expressions involving the coefficients. These are all examples of radical expressions. We'll soon define solvability by radicals in a more formal way, but first we must introduce the concept of fields. A field is just a set of objects where you can add, subtract, multiply, or divide any two elements and end up with another element of that set, with the one exception that you don't need to be able to divide by zero. For example, the set of rational numbers is a field. We denote the set of rational numbers as Q for quotient, which is another word for division. Likewise, the real numbers and the complex numbers are also fields. You might notice that every rational number is real and every real number is complex. We say that Q is a subfield of R is a subfield of C. A subfield is just a subset which is itself a field. We often want to go from a smaller field to a larger one. Suppose F is a subfield of E, we might want to talk about extending the smaller field F into the larger field E. We refer to this idea as a field extension. We write the field extension from F to E, or the field extension of E over F, as E over F. There are a few ways in which you can extend a field, one of which is by adjoining new elements to it. Consider the field of real numbers. How can I extend this field to the field of complex numbers? We can do this by adjoining I. To adjoin I means to consider the smallest field, which contains all of the real numbers, and also I. Such a field must contain all elements of the form a plus bi, where a and b are real numbers, meaning R adjoined I is the complex numbers. We can adjoin things to other fields too. For example, Q adjoined root 2 is the set of numbers of the form a plus b root 2, where a and b are rational. We can also adjoin more than one thing. For example, can you guess what elements of this field would look like? You might guess something like a plus b root 2 plus c root 3, where a, b and c are rational, but be careful, because we can also multiply root 2 and root 3 to get root 6, so this is actually the set of elements of the form a plus b root 2 plus c root 3 plus d root 6, where a, b, c and d are rational. We call Q the base field, and Q adjoin root 2 and root 3 is the extended field. There can be multiple ways to get from a base field to an extended field. We could first adjoin root 2 and then adjoin root 3, or we could first adjoin root 3 and then adjoin root 2. There's also a third way. We could first adjoin root 6 and then we can adjoin root 2, and since root 6 over root 2 is root 3, this new field will also contain root 3. This diagram shows all possible paths from the base field to the extended field. Such a diagram is called the lattice of the field extension. Lattices are very important to the big picture of Galois theory. We're almost ready to define properly what it means for a polynomial to be solvable by radicals. But first, we need to define something called a simple radical extension. Suppose we have a field F. A simple radical extension is where we adjoin an nth root of some element in F. For example, 2 is rational, so adjoining the cube root of 2 to the rational numbers is a simple radical extension. If we chain together multiple simple radical extensions, we get what's called a radical extension. Finally, we are now ready to define solvability by radicals. Let F be the smallest field containing all of the coefficients of the polynomial. The idea of solvability is that if the polynomial is solvable, we can keep adding, subtracting, multiplying, dividing, and taking nth roots, starting with f, to eventually reach all of the roots. We say that a polynomial is solvable by radicals if there exists a radical extension e of f, which contains all the roots of the polynomial. If we consider the smallest field containing all the roots, we can get this by adjoining each of the roots to f. We get what's called the splitting field of the polynomial. Here we call it k. Importantly, notice that since k is the smallest field, which contains each of the roots of the polynomial, and e also contains all of the roots, k must be a subfield of e. Now the final formal definition for solvability by radicals is, a polynomial is solvable by radicals if there exists a radical extension e from the base field f, which contains the splitting field of the polynomial. By this definition, every quadratic is solvable by radicals. If my quadratic has coefficients a, b, and c, then the base field f contains a, b, and c. This means that b squared minus 4ac is in f. Then adjoining the square root of b squared minus 4ac is a simple radical extension, which means that f1 contains negative b plus the square root of b squared minus 4ac over 2a, and negative b minus the square roots of b squared minus 4ac over 2a, which are the roots of the quadratic. This is a radical extension containing all the roots, meaning the quadratic is solvable by radicals. This diagram looks almost like the lattice of the field extension from f to e, but it isn't quite, because the lattice of field extensions needs to include all possible paths from the base field to the extended field. This diagram shows two paths to get from f to e, but there may well be others. We can, however, be certain that this diagram is part of the lattice. It just might not be the entire thing. The goal of Galois theory is to determine when such a radical extension is possible. A group is essentially a collection of symmetries. The group of symmetries of this rectangle consists of these two reflectional symmetries and these two rotational symmetries. This group with 4 symmetries is called the Klein-4 group. A square has even more symmetries. It has 4 reflectional symmetries and 4 rotational symmetries. The group of symmetries of a regular polygon with n sides is called a dihedral group and is written as dn. D3 is the group of symmetries of an equilateral triangle. We'll be focusing on this group for the rest of this section. What symmetries do you think this group has? It has 3 reflectional symmetries and 3 rotational symmetries. I said before that a group is essentially a collection of symmetries, but this isn't quite the full picture. To be considered a group, these symmetries must satisfy some important properties. These properties are called the group axioms. Closure, meaning if I combine any 2 symmetries, I always get another symmetry. For example, if I perform any rotation, followed by any reflection, the result is the same as having done a single reflection. Likewise, combining 2 rotations gives a rotation, and combining 2 reflections gives a single rotation. A group also requires an identity. This is the do-nothing symmetry. Finally, we need inverses. Every symmetry must have another symmetry which undoes it. The reflection symmetries each undo themselves, so they're self-inverse. The 360-degree rotation is self-inverse, because doing nothing twice leaves you where you started. And the 120-degree and 240-degree rotations are each other's inverses, as they undo each other. Since this collection of symmetries obeys all 3 of these properties, they form a group. Technically, there's another axiom called associativity. We will be ignoring this though, as symmetries always have associativity. Finally, there's one more nice property which some groups have but most don't. It's called commutativity, which is where the order of applying any 2 symmetries doesn't matter. If all pairs of symmetries in your group are commutative, the group is called abelian. The word abelian is named after mathematician Abel, who was the first to correctly prove that there is no general quintic formula. There are still a few more things we need to discuss in relation to groups, and then we'll be ready to dive into Galois theory. Just like how we defined subfields, we also define subgroups. The subgroup of a group is a collection of its symmetries which themselves form a group. Our example group D3 consists of 3 rotational and 3 reflectional symmetries. The 3 rotational symmetries themselves form a group. Here we have closure because any 2 rotations combine to form a single rotation. We also have inverses because any rotation can be undone with another rotation, and the 360-degree rotation is the identity element because it leaves us back where we started. The subgroup of only rotations is called C3. What about the set of reflections? Do you think this forms a group? The answer is no, because 2 reflections combine together to give a single rotation, meaning the set of reflections is not closed. There's also no identity element, so this is not a group. This is a shame because we might still wish to talk about reflections in terms of groups, and the way that we do this is by using an idea called quotient groups. Quotient groups are quite abstract and often presented in an unintuitive way. They're very important for Galois theory, so I'll try to make them as clear as possible. For an example, we'll be considering the quotient group of D3, the group of all symmetries of an equilateral triangle, by C3, the group of only rotational symmetries. The idea is to first consider all symmetries of the larger group, in this case D3. Next, we group these together into sets. 2 symmetries go in the same set if there's a single symmetry in the subgroup, in this case that means a single rotation, which takes you from one symmetry to the other. If not, they go in separate sets. In this example, the symmetries in the box on the left are just rotations of each other, and likewise for the box on the right. However, you cannot get from one box to the other with only rotations. You must instead use a reflection to jump between boxes. Each box is called a coset. The idea of what we're doing is essentially that we're considering the symmetries of the smaller group, in this case the rotations, as though they are irrelevant. If 2 symmetries differ by only a rotation, we now group them together and consider them to be the same thing. Roughly speaking, these 2 cosets form a group. This is called the quotient group of D3 by C3. Since the only way to get from one coset to the other is by reflecting, this group essentially holds the idea of reflection. We use vertical bars to denote the size of a group. This quotient group has 2 elements, those being the 2 cosets, so it has size 2. Notice that each coset contains 3 symmetries. There's 1 for each rotation because we can move between elements in a coset by rotating. If we multiply these numbers together, the number of cosets multiplied by the number of symmetries in each coset, we get the total number of symmetries in the original group. This equation can be rearranged. Of course, the same argument works for any quotient group, which gives some more motivation behind the term quotient groups. Don't worry if you still don't fully understand quotient groups, there'll be another example later on. I should also say, before someone in the comments shouts at me for not mentioning it, technically you can't always group the symmetries into cosets as I did here. Whenever you can, the quotient group is well defined, and we say that H is a normal subgroup of G. We'll be mostly ignoring this detail, so don't worry about it too much. There's one much simpler concept we must discuss, and we will finally be ready to dive into the meat of Galois theory. Group lattices are very similar to field extension lattices. To draw the lattice of a group G, start with G at the top and the trivial group at the bottom. The trivial group is the group containing only the do-nothing symmetry. We then write down every subgroup of G between them and draw lines connecting them. You draw a line from a group down to one of its subgroups if there are no groups between them. For example, we can draw the lattice of D3. This is the group of symmetries of an equilateral triangle. We've already seen that the subgroup of only rotations, C3, is a subgroup. There are no subgroups between C3 and D3. The only subgroup of C3 is the trivial group. There's also another subgroup of D3, the group consisting of only the identity symmetry and a single reflection. We call this group C2. You can easily check that this is indeed a group. The only subgroup of C2 is the trivial group. These turn out to be all the subgroups of D3, which you could check manually by considering every possible combination of symmetries. If you want to improve your mathematical reasoning abilities, there's no better course to take than real analysis, where we look at the ideas from calculus, like derivatives and integrals, in a more precise way than you might be used to. That's why I created a real analysis course, so If you're interested, click the top link in the description. Before we get to the core of Galois theory, there are still a few important definitions that I need to make and important results that I need to talk about. The first big word is automorphism. If sigma is a rearrangement of the elements in some field, we call sigma an automorphism of the field if it satisfies the following two properties. Sigma of A plus B is sigma of A plus sigma of B, and sigma of AB equals sigma of A times sigma of B. The reason why these properties specifically will be useful will soon become apparent. Next, the central object of Galois theory, the Galois group. Galois groups are a way to link field extensions to groups. The Galois group of some field extension E over F is the set of all automorphisms on the field E, such that the elements in F remain unchanged. That is, if A is in the field F, then sigma of A equals A. So far, these might all seem like random definitions, but they all come together nicely with this next result. Let P of X be a polynomial. Recall that the base field, call it F, is the smallest field containing the coefficients of our polynomial. When we adjoin the roots to F, we get what's called the splitting field. Let's call that K. When we consider the Galois group of the field extension K over F, the true interpretation of these Galois groups and how they relate to polynomials becomes more apparent. Consider the polynomial equation P of X equals 0. Of course, P of X is a polynomial, so it will look something like this. By definition, this equation is true whenever X is a root of the polynomial. Remember, what the Galois group actually is some group of rearrangements with certain nice properties. Let's call one of these rearrangements sigma. Now watch what happens when we apply sigma to both sides of the above equation. We now use those two nice automorphism properties for sigma of A plus B and sigma of A times B. Finally, we define Galois groups so that the elements in the subfield, in this case that means the coefficients of the polynomial, map to themselves. Since 0 is an element of every field, 0 is in F, which means it is mapped to itself. Notice that the top equation is now the same as the original, but with sigma of X instead of X. This means that if X is a root, then so is sigma of X. Sigma maps roots onto other roots, meaning each element of this Galois group is some rearrangement of the roots of the original polynomial. We often call this the Galois group of the polynomial itself. The Galois group of a polynomial rearranges the roots of that polynomial. We're almost ready for the fundamental theorem of Galois theory, which will reveal the big picture. But I'll first discuss one final important result. Suppose I have three fields. F is a subfield of K, and K is a subfield of E. Then consider the Galois groups of E over K and E over F. If sigma is in the Galois group of E over K, then it's an automorphism on E, which leaves all of K unchanged. But since F is a subfield of K, sigma must also leave all of F unchanged, meaning sigma is an automorphism on E, which leaves F unchanged. That is to say, sigma is in the Galois group of E over F. This is true for every element of the Galois group of E over K, which gives us this subgroup relation. Remember this subgroup relation because it will be important again later. We may then consider the quotient group of these Galois groups, which will give us a very useful result. I never formally defined what a quotient group is, but I gave the intuitive idea. We'll use that intuition to determine what this quotient group is. As a reminder, a quotient group G over H is essentially the group G, where we pretend as though the symmetries in H are doing nothing. Applying this intuition, we have the set of all automorphisms on E which leave F unchanged, but where we pretend as though those which leave all of K unchanged are doing nothing. That is, if an automorphism only moves around elements which are not in K, then it's essentially doing nothing. What happens outside of K is irrelevant. This group is therefore, in essence, a group of automorphisms on K. Since each of these automorphisms leaves all of F unchanged, this is the Galois group of K over F. This equals symbol with a squiggle means is isomorphic to, because technically these groups aren't equal, but they do the same thing and have the exact same structure, so we call them isomorphic. For all intents and purposes, in this video, they're the same group. Also, this fact gives some motivation behind the E over F field extension notation, because it's as though we're cancelling fractions. We're now finally ready for the fundamental theorem of Galois theory. First, consider some field extension, E over F, and draw its lattice. Next, consider the Galois group of that field extension, and draw its lattice. The fundamental theorem of Galois theory tells us that these two lattices are the same, except one is upside down. This is the connection between fields and groups, which lies at the heart of Galois theory. First, I'll explain why this is useful, though you may already have some ideas, and then I'll explain roughly why it's true. Recall that a polynomial is solvable if there's a tower of simple radical extensions from the base field f to some field E, where E contains all the roots. That is, E contains the splitting field k. The fundamental theorem of Galois theory will provide us a way to turn this tower of simple radical extensions into a tower of subgroups. This tower of subgroups will turn out to be much easier to analyse, and we'll be able to show that such a tower is impossible to create in certain cases. You'll see how this works in practice soon, but first, why is the fundamental theorem of Galois theory even true? The idea is to create some kind of correspondence between the fields on the left and the groups on the right. We also need to create a correspondence between the lines in these diagrams. First, we clearly want a correspondence between F and the Galois group of E over F, and a correspondence between E and the trivial group, which is just the Galois group of E over E. This suggests that if I take some field L in the left diagram, it should correspond to the Galois group of E over L in the right diagram. This correspondence gives every field on the left an associated group on the right, but we need to make sure that this correspondence is one-to-one, meaning given some group H on the right, we need to show that there's only one field on the left which corresponds to it. Thinking about what the Galois group of E over L means, this isn't too hard. H is some group of automorphisms of the elements in E which leave F unchanged. It might also be the case that each automorphism in H leaves more than just F unchanged, it might leave some larger field unchanged. We denote this field by E to the H. E to the H is the field of elements in E, such that every automorphism in H leaves it unchanged. This is the only field on the left, such that the Galois group of E over this field is H, meaning this correspondence is indeed one-to-one. We also need to make sure that this correspondence preserves the lines in these diagrams. This is relatively easy to see. Take some line in the left diagram. This line represents the fact that the red field is a subfield of the blue field. This means that the Galois group of E over blue is a subfield of the Galois group of E over red. These Galois groups correspond to the blue and red groups respectively on the right, which give us the corresponding line. We now will see how the fundamental theorem of Galois theory, sometimes called the Galois correspondence theorem, will allow us to talk about this chain of simple radical extensions in terms of groups. Before I do this, I'll make a slight alteration. Currently, each simple radical extension is adjoining some alpha, where alpha to the n is in the previous field. For example, adjoining the cube root of 2 to the rational numbers is a simple radical extension. If you know about complex numbers, you might know that any number actually has n nth roots. For example, there are 3 cube roots of 2. Here, zeta is a Greek letter and represents a complex number not equal to 1, with the property that zeta cubed equals 1. We call zeta the primitive nth root of unity. The idea is that before we adjoin alpha, we first adjoin zeta. This new extension, where we adjoin the nth root of unity, is called a cyclotomic extension. Once we have all of the nth roots of unity already, adjoining alpha, where alpha to the n is in the previous field, is called a Kuma extension. Also note that the field E is not the same field as it was before. Because of these new cyclotomic extensions, this field might be larger than it used to be, but this is okay since it still contains the splitting field K. Each extension in this tower is either cyclotomic or Kuma. Before we pull out the fundamental theorem of Galois theory, you might think that the diagram on screen is the lattice of the field extension from F to E. A lattice must contain all fields between F and E, which this diagram does not necessarily do. We can, however, guarantee that this diagram is part of the lattice. When we use the Galois correspondence theorem, this diagram will be contained within the lattice of the Galois group of E over F. We have this tower of subgroups building up to the Galois group. This tower of subgroups corresponds to our tower of Kuma and cyclotomic field extensions. Notice that if I consider two consecutive groups in this tower, then consider the quotient of these groups, this is the Galois group of one of the field extensions in our original tower, the Galois group of either a cyclotomic or Kuma extension. Is there anything interesting we can say about such a Galois group? It turns out, yes. First, let's consider what the Galois group of a cyclotomic extension looks like. As a reminder, a cyclotomic extension is one where we adjoin the roots of unity by adjoining zeta. We can think about this using our interpretation of Galois groups permuting roots of a polynomial. In this case, we've adjoined the nth roots of unity, zeta, zeta squared up to zeta to the n. These are the roots of the polynomial x to the n minus 1, meaning we're dealing with the Galois group of this polynomial. This Galois group is a set of automorphisms which permute the roots of this polynomial. Let's suppose that sigma is one of these automorphisms. What is sigma of zeta? Since sigma is permuting the roots, sigma of zeta must be zeta to the I for some integer I. The value of I fully determines the behavior of sigma. We can determine where sigma will take any root, say zeta to the k, by using automorphism properties. Suppose we have some other automorphism, tau, which takes zeta to the j. The integer value of j fully determines tau. Now let's see what happens when I apply sigma and tau to some arbitrary root, zeta to the k. If we apply these permutations in the other order, we get the same result because multiplication is commutative. What we've shown is that for the Galois group of any cyclotomic extension, the order in which you apply permutations doesn't matter. We say that the permutations are always commutative. Recall we had a special name for groups like this, abelian groups. The Galois group of a cyclotomic extension is always abelian. Can we say the same thing for Kuma extensions? Let's find out. A Kuma extension is where we adjoin alpha to a field, where alpha to the n is already in the field, and the nth roots of unity are also already in the field. This means that if sigma is in the Galois group of a Kuma extension, then sigma of zeta equals zeta, because zeta was in the base field f. Also notice that when we adjoin alpha, we get for free zeta alpha, zeta squared alpha, and so on. These are the roots of the polynomial x to the n minus alpha to the n. The splitting field of this polynomial is f adjoined alpha, meaning the Galois group we're considering is really the Galois group of this polynomial. Alpha must be mapped to another one of the roots, let's say zeta to the I alpha for some integer I, and just as we did with cyclotomic extensions, we can now use the automorphism properties and the fact that sigma of zeta equals zeta to fully determine sigma. The behavior of one of these automorphisms is fully determined by where it sends alpha. Suppose we have some other automorphism tau, which sends alpha to zeta to the j alpha. We want to show that the Galois group of a Kuma extension is abelian, meaning it doesn't matter which order we apply sigma and tau. These are indeed the same thing because addition is commutative. Let's take a step back to remember where we're up to. We had this tower of groups, which built from the trivial group to some Galois group, and the quotient of any two consecutive groups in this tower is either the Galois group of a cyclotomic extension or of a Kuma extension. We've shown that all such Galois groups are abelian. This motivates the following definition. A group G is said to be solvable if there exists a tower of subgroups from the trivial group to the group G, such that each quotient group is abelian. We also require that these quotient groups are all defined, and as I briefly mentioned when I introduced quotient groups, When this is the case, we say that the smaller group is a normal subgroup of the larger one. This is the definition that you'll see in textbooks. I'll summarize what we've done so far, and then there's one more thing we need to talk about, and then we can get on to the unsolvability of quintics. Let P of x be a polynomial. Call the smallest field containing the coefficients f. Call the smallest field containing the roots k. If this polynomial is solvable by radicals, then there exists some tower of cyclotomic and Kuma extensions from f to some field E, such that E contains the splitting field k. The Galois group of the extension E over f is then solvable. So far, this isn't that useful, since we don't actually know what the Galois group of E over f is, unless we already have a solution in radicals to our polynomial. What we would really like is to say something about the Galois group of the polynomial itself. That is, the Galois group of k over f. We know that the Galois group of E over f is solvable. We can relate these two groups by using a quotient group. The Galois group of the polynomial is some quotient of a group which we know is solvable. It turns out that any quotient of a solvable group is also solvable, which means that the Galois group of our polynomial is solvable. Let's see why this is the case. Suppose G is solvable, that is, there exists some tower of subgroups, technically normal subgroups, so that each consecutive quotient is abelian. Suppose G over H is some quotient group of this group. We wish to show that G over H is also solvable. We need to find a similar tower for G over H. Recall how we slightly more rigorously define quotient groups. We grouped the symmetries in G into cosets. These cosets are then the elements of G over H. For each element G in G, there is one coset N in G over H with G in N. We define the natural projection pi from G to G over H to map each element G to the corresponding coset N. If we apply this projection to every element of a group, Gi, we get a new group. If we project each group in the left tower in this way, we get a new tower of subgroups. Notice that G gets projected to G over H, and the trivial group gets projected to itself. When we do this projection, no important structure is lost, namely the quotient groups are still abelian. This means G over H is also solvable. This means that the Galois group of a polynomial which is solvable by radicals is a solvable group. This means that if the Galois group of a polynomial is not solvable, then the polynomial is not solvable by radicals. We just need to show that the Galois group of some arbitrary quintic is not solvable, and we will be done. We've seen that if the Galois group of a polynomial is not solvable, then the polynomial is unsolvable by radicals. All we need to do to finish this video is to find a quintic whose Galois group is unsolvable. To go into the details of how to do this would require a lot of group theory, so I'll give a summary of the approach. The Galois group of a polynomial P is permuting the roots of that polynomial. If P is a polynomial of order n, then it has n roots. The Galois group is some group of permutations on these n roots. The group of all permutations on n objects is called Sn, meaning our Galois group is a subgroup of Sn. If I choose some quintic polynomial at random, it will most likely have a Galois group of S5. Of course, there are exceptions, but this is to be expected because some quintics are definitely solvable. The way to justify this rigorously involves some other steps involving some group theory, which we don't have time for in this video. We can use this thinking to justify why quadratics, cubics, and quartics are solvable and quintics are not. The Galois group of any quadratic is a subgroup of S2. Is this group solvable? The answer is yes. In fact, it's quite easy to see why. S2 is a set of permutations on two objects. It only has two symmetries, doing nothing and swapping the objects. The only subgroup of S2 is the trivial group. So we get this tower of subgroups. For S2 to be solvable, we need each quotient group to be abelian. The only quotient is S2 over the trivial group. The quotient of any group over the trivial group is itself. and S2 is indeed abelian. So S2 is a solvable group, which isn't surprising because we have a quadratic formula. What about S3? In my previous video, we found a cubic formula, so we expect S3 to be solvable as well. This one is trickier. I'll need to introduce you to a new type of group. Sn is the group of symmetries on n objects. For example, this is a permutation in S6. Every possible permutation in Sn can be achieved by swapping elements one pair at a time. In this case, we needed 4 swaps. Some permutations require an even number of swaps, some permutations require an odd number of swaps. If we consider only the permutations which require an even number of swaps, they form a group. This group is called An. There are n factorial permutations of n objects. An contains exactly half of these permutations. This means that the quotient group, Sn over An, has 2 elements. There's only one group which has 2 elements, that is the group S2. Going back to S3, A3 is a subgroup of S3, and the trivial group is a subgroup of A3. We've seen that the quotient of S3 over A3 is S2, which is abelian. The quotient of A3 over the trivial group is A3. It isn't at all obvious that A3 would be abelian, but it only contains 3 permutations, so it's not difficult to check by hand that they are always commutative. This essentially only works because we get lucky, since 3 is such a small number. What about S4? The quotient group of S4 over A4 is again S2, which we know is abelian. The quotient group of A4 over the trivial group is A4, which has 12 elements. We don't get lucky in the same way as we did before. A4 is not abelian. We need to try something else. Are there any normal subgroups of A4 where both quotients are abelian? It turns out there is one. To find it, let's visualize the group A4 in a different way. Suppose these 4 points represent the corners of a rectangle. S4 is the group of all permutations of these points. A4 is almost the same, but with the restriction that we may only swap pairs of points an even number of times. For example, we may swap this pair and then this pair, which is essentially reflecting the rectangle about a vertical line of symmetry. We can also swap these 2 pairs, which is a reflection in a horizontal line of symmetry. We can swap the diagonals like this, which is the same as a rotation by 180 degrees. So A4 contains all the symmetries of a rectangle. We called this group the Klein 4 group. Could this group complete our tower to show that S4 is solvable? You can check for yourself that K4 is abelian. A4 has 12 symmetries, K4 has 4, so the quotient group A4 over K4 must have 3 symmetries, since 12 divided by 4 is 3. There's only one group with 3 symmetries, that's the group S3, which we saw earlier is abelian. So indeed S4 is a solvable group, and quartics are solvable by radicals. What about S5? It turns out there's only one normal subgroup of S5, that's the group A5. The quotient of these is S2, which is abelian. A5 has 60 symmetries, and it's no surprise that it is not abelian. What might be surprising is that A5 only has a single normal subgroup, that is, the trivial group. So this is the only tower of normal subgroups we can create. The full explanation as to why this is the case requires a lot of group theory which we haven't discussed, but one perhaps more accessible explanation is the following. Earlier we thought of A4 as moving around 4 points, which we thought of as corners of a rectangle. We can do something similar, but much more complicated, with the group A5. Instead of thinking of 5 separate points, we think of 5 separate cubes meshed together like this. It certainly looks confusing with them meshed together in this way, so I added some colours in Blender to make it easier to make out the individual cubes. This shape is called a compound of 5 cubes. Watch what happens when I rotate 120 degrees about the vertical axis. Specifically, notice how the red and purple cubes remain in the same place. The other colours, however, have changed. Specifically, they've cycled. Blue became yellow, the yellow became green, and the green became blue. By using only rotations, it would be impossible to swap only 2 colours. This means that this group is permuting the 5 cubes with the condition that you can only do an even number of swaps. That is to say, the group of rotational symmetries of this object is isomorphic to A5. This shape can be inscribed within an icosahedron, meaning each vertex of the compound of 5 cubes touches the centre of one of the triangular faces. This means A5 is isomorphic to the group of rotational symmetries of an icosahedron. An icosahedron has 20 faces, 12 vertices, and 30 edges. There are 5 types of rotations here. 120-degree clockwise rotations about a face. There are 20 faces, so 20 of these. 72 and 144-degree clockwise rotations about a vertex. There are 12 vertices, so 12 of these each. 180-degree rotations about an edge. There are 30 edges, but since rotating about one edge is the same as rotating about the one opposite, there are only 15 unique rotations of this type. There's also the identity, doing nothing, and there's one of these. These 5 types of rotations are referred to as conjugacy classes. If a normal subgroup contains a single rotation from one of these conjugacy classes, it must have all of the rotations in that conjugacy class. For example, a normal subgroup might consist of rotations about faces, rotations about edges, and of course the identity element. Such a group would have 36 elements. Another important result in group theory is called Lagrange's theorem, which says that the number of elements of a subgroup must be a factor of the number of elements of the whole group. In this case, the whole group has 60 elements, so a subgroup can have 1, 2, 3, 4, 5, 6, 10, 12, 15, 20, 30, or 60 elements, as these are the divisors of 60. We're ignoring 1 and 60 because we don't care about the trivial group or the whole group A5 itself. So a normal subgroup would require that we can choose some combination of these 5 numbers such that they add to one of these. And since every group contains the identity element, the combination of 5 numbers you choose must include 1. There are only 12 possible sums, and none of them are in the green list. This means there are no normal subgroups of A5 other than itself and the trivial group. It also turns out, as I mentioned before, that A5 is the only normal subgroup of S5. That means that this is the only tower of normal subgroups building up to S5. Since A5 is not abelian, this tower is not solvable, meaning S5 is not a solvable group. And that is why quintics are not solvable by radicals. Thank you for watching. If you want to learn more from me, don't forget to click that top link in the description so I can teach you real analysis. See you next time.